What if the stars weren't impossibly far away? What if we could fold space or create a shortcut through it to reach distant galaxies in an instant? Forget everything you thought you knew about interstellar travel. Cutting-edge theoretical physics suggests that manipulating spacetime isn't just science fiction. It might be possible. But does humanity really have a capacity to rewrite the laws of the universe? Or are our cosmic dreams doomed to remain forever out of reach? Right now, Voyager 1, the most distant human-made object ever created, is traveling at an incredible 38,000 miles per hour. Sounds fast, right? But it would take more than 75,000 years to reach the nearest star to our solar system, Proxima Centauri, which is just 4.24 light-years away. Now consider this. The Andromeda Galaxy, our nearest cosmic neighbor, is 2.5 million light-years away. With our current propulsion technology, it would take billions of years to get there. The observable universe extends for 93 billion light-years. Cosmic distances are so immense they challenge not just our technology, but our very imagination. But what if there was a different path? What if, instead of traveling through space, we could manipulate the very fabric of space-time itself? What if we could fold, compress, or even punch holes in reality? This isn't fantasy. Theoretical physicists at institutions like Caltech, MIT, and NASA take these ideas extremely seriously. We're talking about warp drives that could take us faster than light without violating the laws of physics. We're talking about wormholes that would function as cosmic shortcuts through the universe. If you're ready to dive into the most extreme frontiers of physics, into theories that could transform humanity into an intergalactic civilization, or show us the absolute limits of what's possible in our universe, hit that like button now and subscribe to the channel, because what comes next is going to blow your mind. Since our ancestors first looked up at the night sky, the stars have represented the impossible, unreachable points of light, distant worlds beyond any conceivable journey. But humanity has never accepted the impossible as a final answer. In 1969, we walked on the moon. In the following decades, we sent probes to every planet in the solar system. We managed to land robots on Mars, fly past Pluto, and send messages beyond our solar system. But there's a fundamental problem. Distances in deep space are absurdly incomprehensibly vast. Conventional physics tells us that nothing can travel faster than light. This isn't just a technological limitation. It's a fundamental law of the universe, as described by Einstein's relativity. The speed of light, approximately 186,000 miles per second, is the absolute cosmic speed limit. But Einstein also gave us something else. The understanding that space and time aren't fixed, rigid backdrops where events happen. They're dynamic, malleable, influenced by mass and energy. Space-time can be curved, warped, and potentially manipulated. What if the solution wasn't to travel faster, but to make distances shorter? In 1994, a Mexican theoretical physicist named Miguel Alcubierre was watching Star Trek when he had an epiphany. In the series, spaceships use warp drives to travel faster than light. Alcubierre wondered, could this actually work within the laws of general relativity? What he discovered shocked the scientific community. Alcubierre developed a mathematical solution to Einstein's field equations that described a warp bubble around a spacecraft. This bubble would contract spacetime in front of the ship and expand spacetime behind it. The ship itself wouldn't move through space, but space itself would move around it. Think of it like a cosmic treadmill. You're not running faster. You're standing still on a treadmill that's moving beneath your feet. Similarly, a ship in a warp bubble would remain technically stationary in its little patch of normal space-time, while that patch would surf through a wave in the very fabric of the universe. The math worked. Technically, this wouldn't violate relativity because the ship wouldn't be moving faster than light relative to the local space immediately around it. The trick was in moving space itself. But there was a problem. A gigantic and potentially insurmountable problem. To create this warp bubble, you would need something called exotic matter with negative energy density. And we're not talking about antimatter or some rare particle. We're talking about something that possibly doesn't even exist in the universe. Something that violates almost everything we know about how matter and energy behave. Miguel Alcubierre himself later stated that his concept, while mathematically valid within general relativity, is probably impossible to realize in practice. He described his work as a mathematical thought experiment, rather than an engineering blueprint. Kip Thorne, theoretical physicist at Caltech and Nobel Prize winner in physics, spent decades studying the extreme properties of space-time. His work on black holes and gravitational waves helped ground our understanding of gravity. On warp drives and wormholes, Thorne was cautious but not completely pessimistic. These concepts exist at the edge of what's theoretically allowed, but the practical requirements are overwhelming. Stephen Hawking, before his death, proposed the chronology protection conjecture, which suggests that the laws of physics conspire to prevent temporal paradoxes and certain extreme manipulations of space-time. His research indicated that the universe might have built-in safeguards against these cosmic engineering feats. But there's another side. Physicists like Harold White at NASA haven't given up. White revised Alcubierre's calculations and discovered that by modifying the geometry of the warp bubble, it might be possible to drastically reduce energy requirements, from impossible to merely absurd. His research at NASA's Johnson Space Center explores whether microscopic quantum fluctuations could theoretically be amplified to create space-time warping effects. The tradition of physics teaches us something fundamental. The universe operates at scales and with properties that defy human intuition. From quantum mechanics to relativity, we repeatedly discover that reality is stranger and more flexible than we imagined. But we've also learned that there are rigid limits, lines that seem impossible to cross. The question is, are warp drives and wormholes on the right or wrong side of those lines? Now let's talk about wormholes. If warp drives are about moving space, wormholes are about punching through it. The basic idea comes directly from Einstein's equations. In 1935, Einstein and Nathan Rosen described what became known as an Einstein-Rosen bridge, a theoretical connection between two separate points in space-time. Imagine the universe as a sheet of paper. A wormhole would be like folding that sheet and making a tunnel between 2 points, creating a shortcut. There are two main types of wormholes in the equations: traversable and non-traversable. Non-traversable ones would collapse instantly or crush anything trying to pass through them. Traversable ones, in theory, could allow travel through them. But here's the big problem. Keeping a wormhole open would require a massive amount of negative energy or exotic matter, the same mysterious material needed for warp drives. Without it, the wormhole would collapse in fractions of a second, potentially creating a black hole in the process. And there are additional complications. Wormholes could potentially allow time travel, creating the causal paradoxes we mentioned earlier. The accumulated radiation inside the tunnel could be lethal. The internal geometry could be unstable at the quantum level. But perhaps the deeper question is this: could natural wormholes exist in the universe? Could they have been formed in the first moments after the Big Bang? And if an advanced civilization could stabilize them, even if it couldn't create them from scratch? Here's something few people know. There's classified and semi-classified research happening at government facilities on advanced propulsion physics. DARPA, the Defense Advanced Research Projects Agency of the United States, has funded studies on exotic propulsion concepts. Documents released under Freedom of Information requests have revealed that aerospace engineers take these concepts seriously, even though the physics is still incredibly far from practical applications. There's also an aspect rarely discussed: the Casimir effect. This is an experimentally verified quantum phenomenon where two metal plates placed very close together in a vacuum experience an attractive force. Some physicists speculate this represents a rudimentary form of negative energy, albeit at infinitesimally small scales. If we could amplify this effect, scale it up. But here's what you really need to understand. The energy needed to power an Alcubierre warp drive, even with Harold White's optimizations, would still be equivalent to Jupiter's mass converted to pure energy. To create and stabilize a traversable wormhole, you might need energy equivalent to a star's total output for thousands of years. We're talking about Type 2 or Type 3 civilizations on the Kardashev scale. Civilizations capable of harnessing the energy of entire stars or entire galaxies. Current humanity is barely a Type 1 civilization, and there's still one more missing piece of the puzzle. Let's be brutally honest about the barriers we face. First, exotic matter may not exist. We've never observed matter with truly negative energy density at macroscopic scales. All known forms of matter and energy have positive energy density. Dark energy, which makes up 68% of the universe, may have strange properties, but it's not the kind of negative energy required by warp drives or wormholes. Some physicists argue that the laws of thermodynamics and quantum mechanics may fundamentally prohibit the existence of sufficient negative energy. Second, Hawking radiation and quantum instability. Stephen Hawking showed that black holes evaporate through quantum radiation. A similar process could destroy wormholes through quantum fluctuations that accumulate inside the tunnel. As you try to stabilize the wormhole, these fluctuations could grow uncontrollably, leading to catastrophic collapse. The radiation inside a wormhole could reach infinite levels the instant you try to traverse it. Third, quantum gravity, the missing link. Our best theories of physics, quantum mechanics, and general relativity don't fit together completely when you try to apply both to the same system. Especially at extreme scales and energies, the math collapses. Without a complete quantum theory of gravity, we can't predict with certainty what would happen under the extreme conditions necessary for warp drives or wormholes. String theory, loop quantum gravity, and other approaches offer potential paths to unification, but they're still incomplete and experimentally untested. Fourth, the chronology protection conjecture. If wormholes allowed time travel, we could create causal paradoxes. Hawking proposed that the universe has self-consistency mechanisms that prevent these violations. Perhaps the same laws that protect causality also make extreme manipulation of space-time impossible. So if all this is so impossible, why keep studying it? The answer is profound and goes beyond space travel. Every time humanity has pursued the impossible, we've discovered extraordinary things along the way. The quest for philosopher's stone gave rise to modern chemistry. The attempt to create perpetual motion machines established the laws of thermodynamics. The space race produced technologies we use every day, from GPS satellites to portable computers. Studying warp drives and wormholes pushes our understanding of physics to its absolute limits. These studies force us to confront fundamental questions about the nature of space, time, energy, and matter. Byproducts have already emerged from this research. Advanced computational techniques for simulating extreme space-time geometries. New insights into gravitational waves, which we first detected in 2015. Deeper understanding of dark energy and the accelerating expansion of a universe. But perhaps the most important value is philosophical. These investigations teach us cosmic humility. They remind us that the universe is vastly more complex and mysterious than our everyday intuition suggests. They reveal that there are potentially fundamental limits to what any civilization, no matter how advanced, can achieve. And yet, they also show us that reality is stranger and more malleable than our ancestors could have imagined. Who, 200 years ago, would have believed in black holes, the Big Bang, or quantum entanglement? But here's something that will keep you up at night. There are phenomena in the universe we still don't fully understand. Dark energy is accelerating the expansion of the universe in ways that defy our current theories. There are indications that the fabric of space-time might have structure at microscopic scales, perhaps similar to quantum foam. Some physicists speculate about extra dimensions of space we can't directly perceive. And there's strange observational evidence that doesn't fit perfectly into our models. Gravitational anomalies, unexplained signals in the cosmic microwave background, patterns in the distribution of galaxies, suggesting structures at unimaginable scales. What does this mean for warp drives and wormholes? Honestly, we still don't know. Maybe these anomalies indicate new physics that could change everything. Maybe they show us that the universe has tricks we haven't even begun to imagine. Or maybe they just confirm how profound our ignorance is. But there's something else I need to tell you about what was recently discovered. In 2021, researchers at the University of Göttingen in Germany published simulations showing how wormholes could be detected through their unique gravitational effects. If natural wormholes exist somewhere in the universe, we now have theoretical methods to find them. In 2023, theoretical physicists proposed new models of wormholes without exotic energy, using only regular matter in extremely specific configurations. The models are still speculative, but they open possibilities that were previously considered closed. And there's something even more intriguing. Some cosmologists suggest that the Big Bang itself may have created exotic structures in space-time that persist to this day, invisible and untouched, waiting to be discovered or utilized by a sufficiently advanced civilization. The question is no longer just, can we create warp drives or wormholes? The question is becoming, has the universe already created these things, and can we find them? Could advanced alien civilizations already be using these cosmic structures? Could we detect the signatures of space-time manipulation from light years away? What if the answer to interstellar travel isn't building these structures, but discovering where the universe has already built them? This is a story far from over. The next chapters are being written now, in observatories around the world, in particle accelerators, in supercomputers simulating the most extreme conditions of a universe. And one thing is certain, what we discover will fundamentally change how we understand our place in the cosmos. If you've made it this far, you're part of something special. You're someone who doesn't accept simple answers, who wants to understand the universe in its total complexity, in its wildest possibilities and its most severe limits. Subscribe to the channel and hit the notification bell so you don't miss the next chapters of this journey. Leave in the comments, do you think humanity will one day manage to manipulate space-time, or are these dreams destined to remain only theoretical? The journey through the impossible is just beginning.